All right, this morning I want to explain this amazing paper with the title Concrete Score Matching. Generalized score matching for discrete data like tabular data, like language, like graph. Of course, they did it for mainly language and tabular, but I've seen other papers that have used graphs. I mean, they have used concrete score matching, this method of this paper in 2022 for graphs. Oh, again, Professor Stefan Ermon with another beautiful paper. So representing probability distributions by the gradient of their density functions has proven effective in modeling a wide range of continuous data modalities. However, this representation is not applicable in discrete domains where the gradient is undefined. To this end, we propose an analogous score called the concrete score, which is the generalization of Stein score for discrete setting. Given a predefined neighborhood structure, the concrete score of any input is defined by the rate of change of probabilities with respect to the local directional changes of the input. It means that you should define your own gradient for this particular discrete data type, because derivative is defined naturally for continuous domain. But here in this paper, very interestingly, they use this kind of Hamming distance. Very interestingly, they define it for discrete data. So in score matching, we just take integration by parts. So the original score matching loss becomes this loss so that we can train it very easily. But despite their key role in successfully scaling score-based generative models to high-dimensional data sets, we know two critical limitations of existing score matching techniques. First, Phi must be continuous and the density function must be differentiable. This poses a significant challenge in discrete domains. So first, they define this neighborhood-induced graph. They look at, for example, this data point. They see, because you can define a different neighborhood for a data point in your data set. So you can define like this. You can define like this. And there are many kinds of data, as it is. If it can be chain, it can be star, or it can be any other like grid, complete graph. It can be any kind of topology. These are common neighborhood structures, and they're neighborhood-induced graphs. So the arrows point to the neighbors of a given node. Note that the neighborhood structure is directed. Now, using this, they define concrete score based on this. So it's like, this looks like a gradient, but it's discretization of that kind of discretization. Look that this N1, N2, Nk are all neighbors of point X, of this point. So this point X has neighbors, X1, X2, Xn, Xnk, several neighbors, and they are directed. And then they showed here that you can define this, the simplest approach, which is just you define a concrete score like this. So this is the vector. We can obtain the density ratios between neighboring pairs. So given a proposal distribution Q, our sampler, like Metropolis Hastings, our sampler will accept the proposed update X prime with acceptance probability A of X prime condition on X. So we can choose this Q here in the numerator and denominator This is the same thing. This is in the numerator is x condition on x prime, but in the denominator we have x prime condition on x. This is how we define a of x prime condition on x. So this is an acceptance probability. We choose Q to sample uniformly among n, all of the neighbors, given a particular x. When the neighborhood is symmetric, this selection leads to a simplified acceptance probability. So this means that we can also compute tighter bounds, unlike likelihood estimate obtained by unnormalized probability models trained via CSM. Now, they related to this score matching. Now, instead of score matching, we have concrete score matching. Instead of true score matching, we have concrete true score matching. So the idea is very similar, and they have some theorems to make their work complete. This is the proof of the theorem that it says optimizing for is equivalent to optimizing this, which is in the line of work that you have seen in different papers. Now, we propose several modifications to the original training that we found to be crucial for scaling up and improving our approach. We begin with the leftmost term, term 1. So this term 1. So we have two terms. Let's look at term 1. First, we approximate the outer expectation with Monte Carlo samples. Next, rather than evaluating objective for all neighbors, we sample a neighbor uniformly random for every xi in a mini-batch. We then upweight the output form from the model using this sample. Next, we turn to term 2. Term 2, similar to term 1, we can estimate using an unbiased estimator. So you see, for term 1, we use this unbiased estimator. For term 2, we use this unbiased estimator. So they propose another training objective with a focus on computational efficiency using this discrete denoising version of their concrete score matching. We then evaluate the performance on density estimation tasks for a wide range of tabular data sets. Again, they didn't use a graph data set. For example, they use this tabular version of data set. For example, they have different features. For example, brand can be categorical, like Lego or other things. For example, they use Amazon review product. Then you see it has these features. Each feature, the description of each feature is here. And this is the likelihood comparison and discrete tabular datasets. When you see this in any paper, it means higher is better. So they use discrete marginalization and CSM.